Yeah, it's kind of interesting that Euler started going blind when he was around. Triangles on the surface of a sphere. So you're going to see a watermark on this video because I'm using the trial version of my screen recorder, and I'm using the program SketchUp, which is what you see on the screen right now, to visualize this mathematics of spherical triangles. Let's say spherical trigonometry, which can go back to basically Leonhard Euler, 18th century mathematician. Apparently it looked something like this. Famous for this great equation relating the 1, 2, 3, 4, 5 most important numbers in mathematics. Apparently e to the I pi plus 1 unity equals 0. So, but that's not what I'm going to talk about here. I'm going to talk about this other famous equation from Euler: f plus v minus e equals 2, which I won't explain right now, but I will shortly. And Leonhard Euler was a really great mathematician. Anything that I can understand that he did seems great to me. Um, um, he's a contemporary of Benjamin Franklin, basically. But he was born in Switzerland and did most of his work in St. Petersburg, Russia, where he got a job. I don't know what that says about the Swiss, that their greatest mathematician had to work his whole career in Russia, but that's the way it went. But they were basically, just for historical purposes, he's a man of the 18th century. He lived approximately the same lifespan as Benjamin Franklin. Around, he would have been dying shortly after the American Revolution started. Okay, so a spherical triangle is just a triangle on the surface of a sphere instead of being on a plane. So if you take a look at this thing here, um, let's just highlight that and pull off just the triangle, which is something we can do with SketchUp that you really can't do otherwise. So you see you have this kind of curved surface instead of a flat surface, and that has consequences for the geometry. But there's things you can do in spherical trigonometry that you couldn't otherwise do. So send that back and come in here, and I think SketchUp is a good tool, at least potentially, for studying these kinds of things. Let's kind of undo that. So you basically have 3 points here on the surface, A, B, and C, but they're not connected by just straight lines. They're connected by what's called great circles, circles that are centered at the center of the sphere and run along the surface. So that's really the largest circle that you can have on the surface of a sphere. If you just take these, if you take the sphere off, let me just hide that for a second. See what it is? It's just the straight lines between A and B and A and C are replaced by these arcs. So that's the principal difference. All right, so if you accept the idea that there can be triangles on spheres just like there can on flat space, connected by arcs rather than straight lines, and the arcs are parts of great circles, which are circles centered at the origin and having the same radius as the sphere itself. So you have this one, A, B, C, and the first thing you get when you put a triangle on a sphere, or one of the first things you might notice, is you get another triangle on the opposite side. So this triangle is a little bit transparent, so you can see there's another triangular shape that's sort of an upside down version. And what that is, you take the point A, the first vertex, draw a line to the center of the sphere and out to the back surface of the sphere to get to this point A prime, and that's the vertex of the inversion triangle. And then you come here to B, the B vertex of the triangle, do the same thing, and you'll come to B prime, the B prime index, the vertex of the other inversion triangle, and the same thing with C. So you end up with a triangle on each side. And you can pull that off, and since you're working in SketchUp, you can pull that off, just that little, those pair of triangles, and look at them in isolation. And let's just do that. All right, now here are the two triangles just pulled off in isolation in SketchUp, and you can see them quite nicely. A, B, and C, there's the spherical surface, and here are the straight lines through the center of the sphere and coming out on opposite sides. So there's C going to C prime, B going to B prime, and A going to A prime. And you see you just get two identical copies, but that's one is the inversion through the center of the other. And that's just, you know, one difference or one interesting aspect of spherical triangles. All right, another difference that you get when you add a spherical triangle on the surface of a sphere is you get what we can call biangular polygons. You know, on a plane, a triangle is the simplest polygon you can get. You know, closed figure with straight line edges. But on a sphere, you can get a biangular region. And I'm going to show that as soon as you draw a triangle, it's easy to generate three biangular regions that cover up the remainder of the sphere that's not covered up by the triangle and its inversion triangle. So let me just show. There they are, the biangular regions. I just added them. I drew them with these kind of nets here. But what you have is like you have the triangle, let's say at point A, at vertex A, and then you have a biangular region. The angle of the biangle is the complement of the angle A. And I have that, and I'm going to show that how those regions are constructed one at a time for each vertex of the spherical triangle. All right, now I want to show how you can construct a biangular surface at the vertex A of a random triangle on the surface of a sphere. So I just isolated the triangle and the biangular region that I want to illustrate. And the way you do this is you start at the point A, you run a great circle up to C, just like you did to construct the triangle, but you keep going around until you get to A prime. But instead of continuing on the same great circle, because each one of these little lines here is a great circle, I think they're separated by about 2 degrees apart, you turn at A prime and go along here to B prime, and then you come back to A prime. So you can see the angle here. It's just the angle pi, or 180 degrees, minus the angle at A. We can call that angle alpha if you want to. Typically, people call the angles at A, B, and C alpha, beta, and gamma, respectively. So you end up with a biregional area that originates at point A. And you could have drawn it differently. You could have drawn the biangular region by starting to go from A to B to A prime and back along C prime. But that's, you know, you got to either go one direction or the other. I'm just going around clockwise on this particular triangle and starting at A and going to C. And then let me show the biangular regions at B and C next.